We wanted to talk to you today about the emerging architectures of LLM applications in 2025. If this name is familiar to you, it might be because you already have been to one of our webinars before, about a year and a half ago, when we did the same session, when we knew significantly less about LLM architectures. So it's time to refresh stuff. And it's also very familiar from the A16Z article that we're going to mention in a while. But maybe first, let me introduce myself. My name is Gad. I'm the founder and CEO of TensorOps. We are a consulting company, mostly focusing on implementation of AI applications in production. We work with some incredible companies like Notion and JFrog and some other companies that you may have not heard of yet. And we actually have a very, very special guest today. His name is Jeff. Jeff would like to introduce himself.
Hey everyone, how are you doing? I'm super excited to be here today. Gad and Gabriel and all of TensorOps, thanks for having me. I work at Google. I'm a partner engineer, and I work with awesome partners like TensorOps, who, by the way, is super deep in this space. So I'm sure you'll love their presentation. My focus is data and AI strategy with my partners. So I'm going to talk a little bit later today about some cool things that Google's doing. Thanks a lot.
Yeah, glad to have you here. Really, really happy to join. I think people are really going to love your demo. And we also have Gabriel here. Gabriel?
Hey, I'm Gabriel. I'm an AI solutions architect at TensorOps, and it's great to be here.
That was short, but I think people are going to learn to appreciate you over this presentation if they don't know you yet. So what are we going to do to talk to you about today? We are going to talk about agentic workflows, and we're gonna basically overstrike the word agents. We want you to kind of like release yourself from the agent. You will hear a little bit about agents, but we're going to focus a lot about the workflows, and we're going to talk about the underlying architectures that need to support these smart workflows, these agentic workflows. We're also going to talk about the future of LLM applications. So how do we think your applications are going to change in 2025 and the architecture, the underlying architecture that you will need in order to support these changes? And there's some incredible stuff that may have slipped all the Reddit threads and all the tweeters that you've read before. So let's just jump into it. And maybe the motivation for this one is that, as a consulting company or a professional services company, what we go and do is try to go and build applications with customers. And to be honest, with innovation, it's not always easy. Not everything succeeds. But we did notice that one reason for success or failure in applications is that when we're choosing the wrong architecture. And I think a lot of people that are in the same space are experiencing the same thing. You have a lot of buzzwords these days. You have, chat and computer vision and guardrails and RAG and memory and agents. And all of these buzzwords are like, mixing all together. And when you're trying to build an application, it's really about, putting these in the right place. So if you think about even traditional code, right? You're trying to write an application that does something. Maybe it's for ordering pizza. And if you understand the business well, then what you can do is you can wrap the architectural components into components of the software. And then you have a really, you see here like a controller layer and a service layer and a data access layer. And your code and your architecture is really, really organized. And then your quality of program or your software that you're creating is much more, maintainable and has less bugs. And on the other hand, if you don't understand what you're building and what components are supposed to serve, you're getting this spaghetti code. And so what we did at TensorOps is we looked at the architecture that A16Z presented in 2023, which was really, really interesting. But we felt like since then there was some advances that maybe we need to refresh. So if you look at the architecture that we kind of drew for ourselves, we kind of try to map out the components of modern LLM applications. And instead of just going into each and every one of them, we're not going to be able to cover everything today. But what we will do is we're going to show you how certain design patterns or certain products that you might want to build can sit on top of this architecture. So without further ado, I'm going to jump into the first design pattern and the first architecture that you can apply based on that diagram. So if you think about what companies or individuals built up until now, it was mostly chatbots or copilots. Okay, and what makes them kind of unique in the way that they operate is that the user is interacting with the AI on a very short and iterative cycle. So the user is writing a prompt like, what, I don't know, the task that you want to do today. Maybe I want to order a pizza or rewrite my homework. And then it sends it to an application like Gemini or ChatGPT. And then the AI system is going to respond very, very quickly, right? Within 1 or 2 seconds, maybe. And then the user is going and editing it back. And then it's doing these loops back and forth with the AI. And what's interesting about this is that this system is 100% fault tolerant to AI errors. So how can I say that? Because obviously everybody has seen that Gemini and OpenAI, all the AI systems are making mistakes. But the only exit point out of these systems is the human. So the only, the last gateway out of these systems is the human. And this is the most this is probably one of the I would say it's like 9 of 10 architectures that I've seen are either copilots or chatbots, and this is what people built in 2023, 2024. Now, why did this kind of design pattern become very, very popular is that it's kind of built around the limitations of LLMs. So LLMs are incredibly powerful, I don't know, creations, I would say. So it's a software, let's say 100 gigs, maybe 200 gigs, maybe half a terabyte. But within these terabytes, you can create a software that knows how to program better than most of the people in the world. And if it's not impressing you because you're already fairly established developers, not only that it can program better than most of the world that doesn't know how to code, it knows about accounting in Bangladesh better than most of the people in the world. And even some of the accountants in Bangladesh probably are worse than ChatGPT. No offense, it's all over the world. So while LLMs are actually very, very knowledgeable in broad knowledge, if you think about LLMs in the context of your specific application or what your boss told you, so then they're basically useless. So you train them with huge amounts of data, so they have huge general knowledge. But when it comes to what happened a minute ago, or when it comes to what did my boss tell me, what my organization or how my organization handles these kind of cases, then LLMs are useless. And in order to make use of them, you have to provide them with a lot of context. So if you look at this kind of system, what it allows you is the user that has a lot of contextual awareness. So the user might be an engineer working for a company and they want to improve their code, has a lot of context that the LLM doesn't have. And then keeping that closed loop is allowing the AI engineer, the user to basically feed into the AI all of this context in a very continuous way. Now, the other part that LLMs are not so good at is once you give them very complex and long tasks, they get confused. And we call these confusion hallucinations. It's basically errors. So if you think about giving an LLM a really long document to edit, it tends to forget the original task. It tends to omit some cases, some parts of the text. So when you want to do some really complicated task and not just proofread my email, the context of keeping the user very closely in the loop is very, very effective. But, Gabriel, I think you have a word to say about these design patterns.
Yeah, so I think I need to preface this. Most chatbots are lame, not all of them. For example, ChatGPT is an amazing chatbot, but in a lot of cases, people don't go to websites looking for chatbots. And then they're faced with these chatbots that don't necessarily work, and they need to do all the work for the chatbot a lot of times. So in the best case, they're getting an experience as good as talking to a human. And the worst case, they kind of get alienated by this chatbot and then have to go to a human anyway. And now we see in the news that new polls are coming out and people are reporting their thoughts about chatbots, and most consumers don't really like it.
Yeah, so I would also agree that the idea of chatbots is kind of limiting, and this is inspired by LangChain. The idea of people when they're talking about AI is definitely not to think about a system that you need to hold closely in order for it not to make mistakes. And one of the directions that you see the system design working, going towards is systems that can operate by themselves for longer periods. So if you think about LLMs, LLM applications, the best one could maybe operate for itself for like, a year without any human intervention and you just send it the prompt of what it's supposed to do, and everything is doing for yourself, maybe cleaning your house or driving you to Alabama. And one of the architectures that support it is something called the cognitive architecture. There is a really, really good reference to an article that I think you should read about cognitive architecture for LLM agents, for language agents. And we put here the archive. A lot of the slides that you're going to see here are really inspired by their work. But the idea is that we're going to try to take this LLM and we're going to try to give it the ability to work for longer, right? To do more complex tasks and to be aware of what happened before and what's going to happen next. And you see these cases actually make huge impact on customer support already. You see this in coding and software maintenance applications. So I don't know if you're using GitHub Copilot or Cursor, you're going to see these kind of architectures in the underlying of such products. And obviously in what's called AI ops, which is not operations for AI, but AI for operations. And the main components of such an architecture are obviously, LLM, some kind of a memory, short-term, long-term, the ability to do planning, the tools that it might have, like retrieval and do some actions on the environment, and then interfaces. And a lot of the interfaces are about getting these systems to be aware of the general context. And if I really want to focus on how these systems should be implemented, if I'm looking at the architecture diagram that we created or the template for architecture diagrams that we created, these kind of systems would mostly focus on the orchestration. Okay, so let's try to understand why orchestration is so important for this kind of system. This is an example from a chatbot that we chatbot or a co-pilot, I would say, that we built with one of our customers. And what you can see here is the sessions that terminate with errors after the number of iterations that the user is doing with the system. So let me go with you here. In this specific setting, which is the blue one, right off the top, you have about 40% of the sessions that the user is going to say, I don't like the results. But if you let the users iterate more and more with a co-pilot, they basically get more and more satisfied with the results. And obviously, we just talked about why it happens, right? You let the user kind of tweak into the LLM system their knowledge, their context. So the more you let the user work with a co-pilot, the results are getting better and better to some extent. We actually never managed to get 100% satisfaction, and I think it's one of our most interesting insights as a consulting company, which is you don't plan AI systems to perfection. You choose other metrics to success of LLM applications. But when you're trying to talk about agentic systems or autonomous systems, well, what is essentially an LLM, right? It's a prediction model, and a prediction model has errors. So it might look to you very, very accurate, but it has some errors. And the idea of putting it in a workflow means that you're doing each and every step based on the prediction of the previous steps. These systems are called autoregressive. So you have some kind of model that predicts something, and then the model would take the prediction that it made and would build on top of it another prediction, another prediction, another prediction. So it's not one-to-one like autoregressive models like ARIMA, but the idea is that the more actions that you do, even your predictions on average might look okay, the confidence intervals are really growing. So the margin for error is actually getting bigger and bigger because you're building these compound errors on top of each other. So really, when you're trying to work on LLM systems, the question is, how are you going to let them run for longer without compounding this error from one step to another step until you get the kind of sense that, it just doesn't work anymore. And I'll let Gabriel maybe explain a little bit about how can you actually implement that.
Yeah, so this kind of starts with us being able to make the models and the agents plan out their actions so that they can kind of replicate this grounding that we showed in the RAG application to avoid this autoregression and this compound error. So, so a good example of this, and this is a model level grounding, is the new O1 architecture. So we're going to run through an example of this O1 architecture and present the concepts behind it. And the concept that introduces it, it's called inference time scaling. So let's go to the example. So we have this riddle. So a man and a goat are in a boat and are standing on the bank of the Hudson River. They want to cross to the other side. How should they do it? And first, let's analyze what this means. So this is a riddle that is made to be very close to the one with the goose, the beans, and the fox. That is supposed to be a bit more complex, but this is on purpose to be very simple. So the idea is that we're going to confuse the models to give us wrong answers. So if we ask this to GPT-4o, so the conversational model, it will be fooled into thinking we're asking about the other scenario with the fox, and it will answer us with the most likely answer. So in this case, it's going to tell us to take 3 trips, when in fact, after the first trip, the man takes the goat across the river, and he's already there. So you could just stop at the first step.
I love this example because I think it really shows how language, like conversational level models, which is what GPT-4o is really about, trying to emit an answer that looks, textually correct. And in these ones, typically you have a lot of steps, so it tries to make up steps even though it doesn't need it. I love this one.
Yeah, it's a great one. So let's now run this same question through the new, well, not new anymore as AI goes, but the reasoning model from OpenAI. So you see here, we ask the same question. It thinks about it for 1 minute and 38 seconds, which in terms of latency, that's quite a lot. And then it gives us a perfect answer. It tells us that it's close to the other riddles, which is exactly our intention. And then it tells us, in this case, there's no restrictions, so it can be done in a single trip. And that's all. Perfect answer that could only be achieved by stopping, reasoning, and then answering. So this is the type of stuff that these models are going to be really, really good at, and it's often used in maths and programming because there's similar challenges. So more broadly, this presents the concept of inference time scaling. So this is, like I said, a model level planning algorithm. And this technical paper for O1 introduced the concept of a thought period for these models, which is very powerful, as we saw. And the idea is that these models will become smarter with training time. Yes, they still take ages to train and a lot of money. But now, if we scale up the test time or the inference time, they will also become smarter with the increasing budget that we give them to keep trying to figure it out. And so in this technical paper, OpenAI introduced these 2 plots, which kind of illustrate what I'm saying. So on the left, we have the train time scaling with the accuracy. So we give it more train time and the accuracy improves. Obviously, it takes money, it takes time, but we already knew this. But now on the right, we're increasing the test time and the accuracy is also increasing, and quite a lot, as you can see. So this kind of showed the power of this type of models. So it seems that given enough time, it can answer any question. So if we ask it about the meaning of life, maybe it'll take 7.5 million years to figure it out, but I guess it's 42. So,
All right. Gabriel, there isn't a lot of knowledge about what OpenAI is doing behind the scenes, right? And when we're talking about getting models smarter, right, in order to effectively make them uh, be able to do better planning. So we saw that if we want to come up with a better execution plan, if we try to use GPT-4o for that kind of task, which is not a reasoning model or doesn't have reasoning built in, then it might come up with some hallucinations, and then the plan is significantly less efficient. So can you only rely on reasoning level models in order to achieve this?
no, not really. And it's good that you said that GPT-4o doesn't have reasoning built in, because chain of thought, which is what O1 is using internally, was already an algorithm, an orchestration algorithm we were using before with non-reasoning models, and we still keep using it with GPT-4o, 4o mini, and Llama models, right? So the idea here of doing inference time scaling is to, in any way, start spending more tokens to get a better answer. And of course, more tokens means more latency and more cost. And the final answer will be based on a lot of reasoning tokens that are generated, but those often don't really matter. They're just a means to an end. And this is what OpenAI O1 does. So these models, allegedly, it's not open source, but they're reported to have been trained with human-generated chains of thought. So they train these models to explain everything they're doing and then give a final answer and obfuscate this chain of thought. So the user of these reasoning models will never see this final chain of thought. So this, as we can see here in this graph, the idea is that now the inference will take a much larger chunk of the total time that the model takes to work in total. But this is not the only way to do it, like we said. So there are ways we can do this without fine-tuning a model specifically for reasoning. So we can do this in many approaches. Google released a great paper on the different methods to do it and the optimal way to do it in August of last year, ages ago in AI terms. So it presented three main approaches. The first of them is best of n. So the idea is, instead of generating a single response to a problem, we will generate n responses and then create critiques for these responses, and then use these critiques and the responses to produce a final better one. And this increases, this does two things. It increases the accuracy quite a lot in more complex issues, and it also allows us to customize n to the budget that we want to give this reasoning model. So more responses will be better accuracy, but more latency and more cost. Another approach for this, and it's a bit more complex, is to do kind of best of n, but on a tree search algorithm. The idea is you start with a problem, you do some kind of reasoning, you go through a step of this problem, and then you use a model to evaluate how good this reasoning was, and then expand the better nodes of this tree. So as you can see in the figure, it acts, it gets 0.6, there's only one, and then there's two nodes, 1.8, 1.4, and then it expands that one, and then it keeps doing it iteratively. And this will essentially result in you always expanding the best thoughts iteratively, and in the end, you end up with a very good chain of thought that gets you to the right answer at the end.
So if I'm thinking about the first agent, for example, in LangChain, sorry, it was the React agent, which kind of introduced the concept of a loop, right? One step is chain of thought, and then you go and do these actions, observe what you got, and then reflect back to the agent, and then do another chain of thought, and you do this kind of loop. So essentially what you're saying to me is that you can create this loop in a more sophisticated way.
Yes, and basically have many thoughts and discard the bad ones and expand the good ones. I wish I could do that myself.
Why would you do that? So when you have a model like Gemini 2.0, which it has reasoning built in, why would you need to go and do that outside of the model?
Because it's another way to increase accuracy. So if you have a very good model, it's already going to be, let's say, 80% accuracy. But by adding this tree search, you will be removing the worst answers that it gives. And within that 20%, you might be able to save 5% more of accuracy, which for your use case might be extremely valuable.
Okay.
And a good example is, let's say you're building an AI product. You're not supposed to get to 100%, but if your requirement is 80 and you're at 78, maybe this is the one that saves your project. Okay. So it's always useful to keep in mind.
Okay, go on.
So another simpler way to do this inference time scaling is to do something that we even spoke about before. So it's called iterative refinement. And basically, instead of generating one answer, we keep refining it until the end, until we are happy with the answer. And the innovation that Google presented in this paper is that we can also do this in parallel. So the more parallel threads of improvement we have, the more budget and the better accuracy. And then in this paper, there's also an interesting quote. So basically, Google defined what's compute optimal scaling of this type of inference type scaling. And they defined that easy questions and medium questions benefit more from this approach, and very hard questions that the model wouldn't be able to answer won't be saved by this approach. So the idea is this allows you to increase accuracy, but it won't make your Llama 7 billion model beat GPT-4o. It's just another way to slightly increase the accuracy, or increase the accuracy significantly, but it has a plateau.
All right. So when we're talking about orchestrating, if I go back to, maybe I'll jump back a few slides. So the idea of this architecture is that, we have here something that you might call an agent, and you have that loop that is the reasoning loop. And effectively, in order to keep the whole thing going, you need to come up with a plan on what's supposed to be your next action. So we talked about having an LLM that would be in place to make this decision about the future, but not, and there is this question of, do you still need a loop? Are you still going to need that like cycle, which is external model? Are you still going to need that, you know, reasoning and planning and orchestration that is external to the model? Because what you've seen in GPT-4o, for example, is that it comes up with a stupid plan. And then when you move to a smarter model, you don't need any more, steps like think step by step, or you might have implemented in the past some kind of a reflection on top of GPT-4o just to make sure that the plan makes sense. And then, another model would inspect it. So all of these like looping, is it still going to be required? And the answer is probably yes. Because as we said, some of the stuff is definitely going to stay at the model level. The models are extremely intelligent in, generalizing on stuff, knowing what to do inside the context of what they were trained. But when you have a specific system that you want to that you want to build, so you have a user and maybe you have some Python logic, business logic that you want to implement, there is need to be a way to go and combine all of these components of the product that you're trying to effectively build, whether it's going to be like a chatbot for automating customer requests, or is it going to be a code assistant? And there are two design patterns that we're starting to see as emerging and leading the industry. Now, I will say there's going to be a few provocative stuff that maybe people from LangChain are not going to be so comfortable with, but we'll try to address them in the best way. So on the left, you're going to see the concept of graphs, and LangGraph as one of the best, or one of the most emerging tools for agent architectures, is basically going to allow you to build a graph, and the orchestration is done through traversing this graph and deciding on the steps. And we're going to see a few design patterns that this technology allows. So LangGraph, by the way, if you don't know, they were inspired by NetworkX. And then there is another design pattern, which is more message-based. And if it sounds familiar to you, it's because if you think about traditional orchestration, so let's throw out LLMs for a second out of this webinar. And if you think about traditional software, how do I orchestrate stuff? And there's two design patterns that really came to dominate. Stuff which is graph-based, like maybe Airflow. So if you think about, you have an ETL, you're going to use Airflow in many cases to orchestrate your processes, your data processing. And there is another one, which is event-driven. So instead of defining explicitly the graph, you're going to make triggers to event, and effectively these triggers are going to be consumed and some other components are going to use this. So if I'm thinking, again, in traditional software, these are two design patterns, and we should probably look at them and try to understand how they were built and what purpose they serve in order to understand how we're going to implement them now in the domain of AI. So let's start with graphs. And like I said, a LangChain is built on the concept of graphs, or sorry, LangGraph is built on the concept of graphs. I will say that it is using underneath an event-driven architecture. So you can basically do everything which is event-driven on top of LangGraph, and they even added some more advances recently that Gabriel is going to mention. But the idea is that if you kind of know what's the workflow that you're trying to implement, then graph-based orchestration is exactly the kind of technology that you would like to use. So this one is inspired by Anthropic. They recently released a really, really good blog post called Building Effective Agents. And the idea is that you're expressing the kind of business logic solution in the concept of graph, and you may want to introduce LLMs as part of these components. In some cases, the LLMs can be processors. So imagine for yourself that the LLM is maybe doing some kind of classification to the text, but the flow is being determined in advance on the graph. In some cases, you can build some more complicated architectures, like this one, like the orchestrator synthesizer, where the LLM is actually deciding to which LLM to call, and then there is another LLM that does synthesis of these of the outputs of the previous steps. So you can build graphs in which LLMs are participating as part of the compute power of the graph, but also kind of like dynamically choosing where to route the graph. So either you add some more dynamics into the way that you're doing the orchestration. What's interesting when you're starting to do this kind of stuff, so graphs are really great because you can think of each graph as an instance of your orchestration. And once you are orchestrating a graph, you're orchestrating basically a process. So this is when you look at OpenAI Assistants API, basically when you're launching an assistant, you're launching a job or you're launching what they call a run. So effectively what you can do is kind of use this concept of runs and jobs in order to start to monitor all of these crazy AI applications that are running as separate instances. And graphs are really, really, really nice way. And I think that LangGraph chose a really, really good way into starting to expose the world into agentic workflows in the terms of in these terms of graphs, because it's really easy for developers to think in edges and nodes and how to connect them and what's supposed to be the first step and the next step. But to be honest, it is quite limiting in the way to in their way to express a complex idea. And I'm going to give a good example to. So in an event-driven architecture, which is the other kind of design pattern that I would like to mention, and I'm going to make it more clear what's the difference between them. So imagine a system where an employee is being onboarded on some kind of an onboarding system. The idea is that that would emit events, and it would send it to Google PubSub. And on top of that, you'd have subscribers. So for example, a system that allocates email to new employees and a system that would issue badges. And in this case, the system that emits the event that an employee was onboarded, it has no idea what are supposed to be the next steps. And it's the responsibility of the consumer to know what's their job once an event is reaching to them. And I think that you're going to see more of these architectures and more of these designs as you would like to build more complex systems. So imagine, for example, that you're trying to build an code assistant. And this is, by the way, taken from the Anthropic blog post. I forgot to put a mention, but we'll put it afterwards, maybe in the slides. So if you think about, I want to write a code assistant. All right, so maybe my first action when I'm trying to build a graph with all the components, with all the nodes, my first action is quite simple. I'm going to start writing the code. Okay, and then when you're trying to decide what's going to be the next action, so is my next action going to be to run the code, maybe to test the code, maybe to write a test for the code and then run the test and see the results? So it's quite difficult to understand what's the right order to call these nodes in the graph of the execution. And you would like to be able to communicate a more dynamic way of processing this task. So in these cases, what I would think would prevail is eventually a much more loose architecture, which is purely event-driven. And I will say that when you're looking at what Llama Index is doing with their workflows, it's also event-driven, and there is also a way to build graph, right? So if you say, draw all the possible flows, eventually it will create a graph. But, and Gabriel, maybe LangChain is also doing this, right?
Yeah, so in its backend, LangChain is just a LangGraph is just a pub subsystem. But they expose kind of two interfaces these days, and I wanted to use those two interfaces from the same backend to show you the different ways to program agents. So on the left here, we have what's the normal LangGraph way to do things. This defines a typical React agent. So you see we add nodes, which are functions. So the nodes are the call to the model, call to the tools. And then we add the normal edges. So from the tool, you go to the model. And then you start to add conditional edges. But now I want to add another agent. So let's say my agent needs to call another agent. The only way to really do this elegantly here is to add the agent as a tool of my first model, or to add more conditional edges. And very quickly, this starts to kind of break down and your code is not going to look so good. So this is what LangChain is now doing with what they call handoffs. And Llama Index has done this with their workflows from the start. Instead of defining the graph beforehand, what you'll do is you'll have an agent function that runs your normal agent. Then at the end, you will return the next node where you're going to go. So in this case, in the goto, in the command being returned, you could return the next agent and provide this update parameter, which will provide it a custom state. So it's much easier to do a handoff. That's the pattern that we're trying to implement here.
Okay, so I will say that LangGraph is built on top of event-driven architecture, but effectively, once you actually need to define, and many of these agent frameworks that you're seeing these days, they do the same. You're basically defining the node, and then in the end of the node, you are kind of enforced to decide what's going to be your next step. Even if this decision is LLM-based, it's still pretty much enforcing. And if you think about event-driven architectures, there is one that is more close to like graph orchestration, which is called point-to-point, which is a lot of what the architectures that we are seeing are implementing. I think that what we will start to see in the upcoming year is much more pub/sub kind of way of communicating, publisher subscriber, where the node that releases the message doesn't know who's going to consume it. So you would see an agent releasing a message to the message bus, and then other agents are going to consume this message and decide what to do with it without you as a developer really thinking if you're going what needs to happen or how you code the logic. And obviously, it's a bit presumptuous to say this because the graph is simplifying a lot, and it helps you kind of like constrain the system and ground the system. So I don't think that graphs are going to die. So if you look at traditional software architectures, graphs and event-driven architectures still survived. So I do think both of them are going to survive. It's just that for the more complex architectures, I think pub/sub is going to be much more adequate. And with that, I want to present a completely different approach. Okay, so we kind of discussed about how agents is not really a thing, where what we think you should really, the terms that you should really think about is smart workflow orchestration. So you're taking complex workflows that represent business problems and you let AI solve these problems. So it's less about the agent and it's more about the orchestration. And we presented one direction that like the industry is going into, which is longer and longer processes. But maybe if we go back to that drawing that we saw the user interacting with the AI in a very close interaction. So the user is sending requests to the AI, it's waiting, it's going back to the user. Maybe there is going to be a completely other direction in which the user is actually working even closer to the AI. So instead of releasing the AI into the world and just saying, come back to me with results in 5 days, like 42. Instead of it, the AI is going to work much, much closer to the human. And we are going to see a few of these cases that Jeff is going to share with us. So yeah, agents is like one direction. I would let Jeff kind of build this story. And I think he has an incredibly interesting demo to show. Jeff, are you ready with the screen sharing?
I am.
Okay, so I'm going to stop sharing and I'm going to let you.
Great. Okay. Yeah, thanks so much, Gad. So it's really interesting what you're talking about on the agent side of things, because where we at Google are seeing things going, and it's really industry wide, there is the notion of agents in the typical chat space where it's essentially augmenting what you're trying to do as a person, whether it's in your job or personally. You're chatting with this agent or you're showing it video and you're basically asking it to enhance your knowledge about something, to generate something, help you solve a problem. Then there's more of the workflow agents, as you were mentioning, where let's say there is a very smart chatbot or agent for retail or for an insurance website where there is still a flow that has to occur in order for the agent to succeed in its activity. But yeah, definitely. So I want to talk a little bit about multimodal and what we're doing at Google right now. So I'm sure that a lot of people have already heard about Gemini 2.0. It's been released experimentally, and the great thing is everyone can try it for free. There's 3 ways that you can do that. AI Studio, which I'm about to show you. You can also use our end-to-end LLM ops platform, which is Vertex AI. And you can also hit it directly using the SDK of your choice. So I would really urge everyone to go try it out. The full multimodal capabilities are there. So what does it actually mean though? Basically, a lot of us have been interacting, let's say a few years back, and even as recently as last year, you're sending text to an LLM, and then you're getting generated text back, or you're sending text and you want audio back. Similarly, in the inputs, maybe you're uploading something like audio or video and waiting for some processing to occur, either as a batch or something that's synchronous. The really nice thing about Gemini is it's multimodal by design. So what we've done is we pulled in all the different modalities you see on the left for the inputs, and Gemini doesn't really care too much about what you're sending it. It's all API driven and capable. And as of now, with the experimental version, you're getting text and audio on the output. And if we start talking about what you can actually do with that, when you add to some of the features of Gemini, it's also natural interaction. So again, this used to be much more of a synchronous flow where you ask a question, you get a response. If you're unhappy with the response, you ask another question, and that sort of flow. The really great thing that's happening with Gemini 2.0, which is enhancing the agentic AI era, is there's an open socket now. And you'll see this shortly in my demos, but you can now use that open socket, either API driven or if you're using it in the interface, and you can essentially stop Gemini in its tracks and have it update something or tell it you think otherwise, and it will respond as well. So some of the other great features, combination of Gemini 2.0 and the platform or Vertex AI, which supports Gemini. Responsibility. This is something that is extremely important. The patterns that we're seeing a lot with many of our customers are, let's say the last 2 years was the prototyping phase of using LLMs for companies of any size, really. Let's get something up and running. Let's get an MVP. Great, it's working. Let's now get that into production and we'll fix the problems later. As you can imagine, a lot of problems, and there have been many famous examples of this. Bad things have happened. You might be getting back hallucinations that can be hurtful. You might be getting back hate speech, or even worse, you could be a bad actor trying to generate hate speech or instructions on how to do something which could cause harm. So the great thing about Gemini 2.0 on the Vertex platform is we're taking a lot of that into account for you. So you're not having to, let's say, build that yourself. Um, the other thing which I was just mentioning, of course, you have now the live streaming, which I'll show you in a few minutes. And to build out on Gad and Gabrielle's points, from the agent side of things, Gemini 2.0 is enabling the functionality for the reasoning and the tools and the grounding. Finally, you'll also see governance, and we're going to go into that in a little bit as we talk about Vertex AI. So Gemini, through some of these demos that you'll see, there's things like built-in code execution, where it can execute code inside of a virtual environment, but literally show you what it's doing. It's not generating textual outputs, it's actually executing something. In addition, you can do the function calling. So this takes things beyond generating responses, but you can also through common API sets, open API, you can execute activities. So you're giving Gemini 2.0 a chance to interact and perform actions rather than just providing information. Finally, what's really, really important and is a pretty amazing thing that we recently announced, the grounding functionality where you can ground in Google search. So what this will help you with is when your agent or your LLM calls need to go out to the internet, if there's any information that's real time or past the date of training, it can go ahead and do that through Google search. And there'll also be footnotes to show you where that came from. And as expected, we have different RAG optionality and Vertex AI search, which is going to be GA shortly. That just takes care of the vector embeddings for you so that way you're not having to build it out yourself. So with that being said, let's take this for a spin. So I have a couple of demonstrations that I've gotten ready here, and let's go ahead and start. Okay, great. So I'm sharing now. Welcome to Google AI Studio. Think of this as your rapid prototyping environment where you can execute a lot of the functionality that I spoke about. You can really start enjoying a lot of the features of Gemini 2.0 with very lightweight capabilities. So I'm going to jump right into the multimodal streaming. So if you haven't seen this before, it's really cool. I hope you enjoy it. Let's start. Hey, Gemini, how you doing today?
I'm doing well, thanks for asking. How can I help you today?
Great. What am I wearing?
You're wearing a black hooded sweatshirt with a Google Cloud logo on the right side. It also has a circular patch on the left side.
Yeah. What do you see on the patch?
The patch on your sweatshirt has a Google Cloud logo and says Certified Professional underneath it. Yay.
Nice. Based upon the swag that I'm wearing, where do you think I work?
Based on the Google Cloud logo on your sweatshirt and the Certified Professional patch, it's likely you work at Google Cloud.
Okay, good guess. Let's jump to another thing. I've had a really busy day. Unfortunately, I wasn't paying attention when I was driving home. And if you look at my phone, this happened. What do you see there?
It looks like two cars have collided. There's a light blue Tesla and an orange car with damage to the front bumpers.
Yeah, is there a lot of damage to that Tesla? Assume that everything that you see is the scope of the damage.
Yes, there does appear to be a significant amount of damage to the front of the Tesla,
That's too
specifically the
bad.
bump.
I'm probably going to need to get this towed. Can you recommend uh, a tow truck company in San Francisco?
Sure, here are some towing companies in San Francisco. B and A Towing Service.
Awesome.
They are a full.
That's great. I'll call them in a minute. What about repair shops? San Francisco again.
Okay, here are a few options for repair shops in San Francisco. The Garage SF. They offer complete auto repair and body shop services.
Excellent.
And
Last thing, car rental, San Francisco. Is there anything that you can recommend?
sure, here are some car rental companies in San Francisco. City
Awesome.
Rent a Car.
So let's switch gears real quick. I also happen to be a developer, and I was looking at this code today. What are your thoughts on it? What does this do?
That code appears to be using Python to access a Google Cloud Storage image and then send it as a prompt to a multimodal model to generate a blog post.
Very cool. Let's change gears one more time. I love science fiction shows, whether it's movies or series, and I also enjoy watching dystopian shows. So, based upon this list here, what do you think I should watch tonight?
Based on your love of dystopian and science fiction shows, I would recommend you watch Silo. It's a science fiction show that is #1 on the top chart of TV shows.
Great. Were there any others?
Yes, Shrinking is also listed on the top chart of TV shows, and Severance as well.
Ooh, Severance
Dot.
sounds cool. The only problem is I don't have I don't have a subscription to Apple TV Plus. Can you recommend any other providers to watch this?
Severance is exclusively available on Apple TV Plus.
Mm,
However, it's also available to rent or purchase on Fandango at Home, Amazon Video, and FlixFling. It can also be streamed for free on Hoopla, Plex, and Plex Channel.
sounds great.
Purchase.
Okay, so that was a lot of fun. We did a lot of different modalities there, a lot of different reasoning there. Um, and think about modalities inside of modalities. I was showing a picture of crashed cars through my video session, and Gemini is able to really understand what it's looking at and to reason, make assessments, call external tools. And I'm not sure if you saw the background while it was doing this, but there you could actually see the debug of the external function calls and the code execution it was doing. So there's tremendous amount of capability with Gemini 2 out of the box. The API is available, so I would really urge you check out the documentation. We also have a Google provided example set on GitHub
You're
where you can
still,
see them.
you're
Go ahead.
still, sorry, you're still showing the Gemini. If you want
Yeah.
to go back to the deck.
Yeah, no, I'm about to switch back. I'm just kind of filling in some details here. Thanks. Yeah, so there's a lot of other options, but I would definitely urge you to check out the GitHub. We can send that out to you also. So a couple more slides here, and then I'll turn it back over. Um, so I wanted to talk about the end-to-end development, which is Vertex AI. So as Gad showed you before, there's a lot of complexity, rightfully so, for managing LLM operations. And this isn't just a pattern for LLM ops. You have this for ML ops. You have this for DevOps. You have this for working with infrastructure. Whatever it is, there's always going to be a process that you need to follow to ensure consistency, governance, controls, repeatability, you name it. And while all this is definitely possible with common open source tools, a lot of patterns that we see, going back to my talk about, a lot of companies have been experimenting in the past few years. A lot of them have MVPs. This is the year where the majority of organizations will now start having full production, whether it's externally facing to your customers or internally facing to your internal users. There will be full production systems. It is now more important than ever to make sure you're properly taking care of these systems. So as we talk about things like, and by the way, this is the Vertex AI logo. As we talk about things like the agent runtime, of course, Gemini 2.0 that's landed inside of Vertex AI, as well as the different reasoning. The tool sets, all of those tool sets that I showed you on the previous slide are enabled inside of Vertex AI. When we talk about the data, whether it's a vector, whether it's a custom data source, that all is also going through Vertex AI. LLM operations, super important. So all of the prompt management, the versioning, the logging, that's through Vertex. AI safety, we spoke about the importance of that through responsible AI. You'll get that too. LLM, so it's not just Gemini 2.0. We also have a full model garden with well over 100 various sourced models that you can choose from. And of course, fine tuning, data set management, experiment tracking. These are all aspects of your operation cycle that you can manage inside of Vertex AI. So I've been talking to a lot of our customers recently about how they make the jump to an organized and governed way to run their LLM operations. The good news is your notebooks, if you've been doing a lot of custom coding, you can bring those notebooks right into Vertex AI, and you can really hit the ground running. And from there, you expand out and put together the proper guardrails and processes. So key takeaways. I hope you've been inspired by what you've seen in the demos, and of course, what has been presented by GAD and TensorOps. We are definitely well into the multimodal era right now. Gemini 2's announcement really makes that loud and clear, and it really is delivering the message of, Google is your AI platform. Agentic AI, this is a growth driver. So don't think of agentic AI as just an internal efficiency driver. Thinking about various workload processes internally to shave off time or to improve SLAs. This is also something that is externally facing. Like if you think about the example I put up with the damaged vehicle, imagine car insurance companies using similar workflows, et cetera. Finally, Vertex AI can handle the end-to-end platform development. So if you're getting overwhelmed, if the open source LLM ops is not your core business objective, and your developers and your data analysts are starting to get bogged down, this is something to think about. So with that, I'm going to close off. But thank you all so much. I'll stop sharing.
Right. I'm gonna take it over. And I got in the meantime a question on a private. By the way, if you do have questions, you are more than welcome to just ask them. I got a question of what is multimodal and why is it different? Maybe Jeff, would you like to take it or?
Yeah, absolutely. So if what are modes? Modes are the various channels of interaction. So typically, you would think about the very beginning of some of the models that were out there. You would send a text message to the model, and it would return back generated text in return. Or you would send text and ask it to make a picture, and you would get a picture in return. So now with the same model and at the same time in the same stream, you can inject into that text, video, audio, and of course, pictures as you saw. And the model in the same session is able to interpret all of that. So what's happened with Gemini 2.0, it's brought in the capabilities of what would previously take multiple models. And of course, on the back end, it's doing that in an agentic fashion. If you noticed some of the coding going across the screen during the demo. But multimodal is multiple ways to interact on the input and then multiple ways to get your response on the output.
So I I love this response. I think in terms of architecture, what it means to most of the people that are going to build AI applications themselves is that a lot of the stuff that you had to do before, for example, if you designed a copilot and you would upload the image and then the image would go to processing in one model that would turn it into text, and then the text would be transformed in an LLM to an answer. Now we can send it all to one model that has like this unique representation of all the data together. So it simplifies a lot the architecture. And I think one of the major takeaways that I have is that everybody's saying 2025 is going to be the year of agents. And a lot of the stuff that you're going to see is a lot these agents that you send a message to, and then they are going and operating for a long time, and then they're giving you back this answer. You see OpenAI saying, we have a model that can think about for like 3.5 days, and then it gives you back the answer. Where I think the more interesting product angle is not AI that goes and does stuff. Everybody understand it. There is going to be a huge bunch of implementation of autonomous AI systems. But I think what might be missed out is that collaborative, interactive way of working with computers. I see somebody mentioning Anthropic has this, computer operator that's a nice demo. I think you just saw Google. By the way, there is a great a demo of Gemini 2.0 co-coding, like does co-programming with a developer. We're going to send it to you afterwards. And you can also see this one in LangChain, for example. So this is a great example of another interactive way of communicating. This is it's called Canvas. And the idea is that instead of going back and forth to the model and creating a lot of grounding and planning and orchestration, you effectively shorten the interaction time with the user to make it really, really, really smooth. Okay, so we are just about 1 hour into this webinar. I gotta be honest with you, we have quite a lot more slides to go. And this one is going to be very, very, very deep. So brace yourself. If some people need to drop because it's already late in their time zone, we really appreciate it that you come, but we are going to just continue with some more, I think, nuances especially to the previous, to the first deck that we showed, which is the long-running agents or the long-running agentic workflows that we described. So, and again, thanks a lot, Jeff, for the demo. I think we're getting these incredible messages here, both in public and private chat. So thanks a lot. So, we've shown you two technologies, and very often when you're showing technologies, it's quite easy to imagine what they could turn into. Right. So a few years ago, we discovered that AI or neural networks can press the pedal and maybe they can also steer the wheel. So, cars are going to drive themselves automatically in 2 years. And then maybe a few years ago, we discovered that neural networks can discover tumors in radiology imaging. And then say, well, like, radiologists are going to be obsolete in 5 years. And, 2024 came and still radiologists are riding their cars to work, driving their cars to work. I don't say that this technology is not going to evolve, but sometimes technology takes a little bit more effort than what it looks like. And we wanted to kind of show you where the stuff that we've shown you before as like this emerging cognitive architecture and amazing architecture, where can this get more complicated and what can you do about it, including some very, very tricks and errors that we've seen companies implement and ways to work around them. So Gabriel, I'll give that to you.
Yeah, thanks. So I wanted to go again into the Koala agent framework. We briefly spoke about it in the initial slides and used a lot of their diagrams. This paper is just such a great source. And I wanted to deep dive into some of the components that are listed there, because I think it's important to kind of talk about some of the pitfalls and some of the technical challenges with each of these components. And it kind of establishes in this paper a great framework for what an agent is and what an agent should be. And if you know this by heart, you'll probably build some very good agents from now on. So I really wanted to get this one across. So sorry. So the main components for an agent to work well, the three main components are memory, action space, and decision making. For memory, we're going to have two types, long-term and short-term. We will deep dive into them in a short while. And for an action space, we have four main tools that are going to be reasoning, retrieval, learning, and grounding. And then the decision-making is where most of your LangGraph code and orchestration code is going to be at. So we're going to start with memory right now and kind of do a deep dive into memory. So for short-term memory, what do we want our short-term memory to be? We want to keep track of the current conversation. So think of it as the list of messages that your agent will keep track of. So human AI interactions. And it should also allow these conversations to be resumed if they're interrupted. Kind of like ChatGPT does it. You can just press one of your previous threads.
So this is like, LangChain implemented memory for the chat.
Yeah, the most basic list of messages you can have. Of course, there will be some complexity down the line. And then you have long-term, yeah.
And that is because LLMs are effectively stateless, right? So you're putting in to the LLM some text, it makes prediction, and then it doesn't remember what it did before. So you have to implement it externally as some kind of a data-based array in the memory.
Yeah. Otherwise, the LLM has no idea what's going on in your conversation. So you always need this short term. So
far, you sound to me like 2023. I'm guessing the next one is going to be more innovative.
Yeah, that's where it's interesting. So long-term, this paper, in long-term memory, this paper kind of splits it into three types of long-term memory. And it's inspired on our brains, how our brains work. So we have an episodic memory, which is going to save things that happen. So today I went out and it was cold. It's going to have a semantic memory, so things to remember, like definitions, things in general. And you're going to have procedural memory. In humans, this usually relates to muscle memory, how you move around, how you do the most basic things that you don't even think about. So it's kind of like not stuff you don't think about. So let's go into short-term memory. So we want to keep track of the conversation, like we said, but there are some complexities to this when we start getting very, very large message threads with LLMs. So let's say we're talking to ChatGPT for a year, right? The thread is going to be crazy long, so you need to do something about it.
I mean, I don't want to be rude to like OpenAI, but ChatGPT would probably get filled much easier with their context window. Gemini 2.0 with a $2 million context size window, it's gonna get filled in a year. So just gonna say.
So let's say you speak to Gemini for 10 years. Eventually, it will be filled.
It will run out of memory.
I've tried to speak to it for 10 years. It's I'm getting there.
Yeah, it's in 10 years, I think it will be a problem. We'll have billion token context windows. So let's see, we have three main options in this case. So the first is we start dropping the first few conversations as like a sliding window. So the old conversations start to be completely deleted because they don't fit anymore. But this kind of can cause this model to look a bit dumb because it forgot things at the beginning of our conversation. So the user might kind of be shocked by the fact that it doesn't know it. So this is the naive approach, obviously. And then there's two other options that kind of require post-processing of your context window, of your short-term memory. So one of them is to use an LLM to filter out irrelevant messages. Realistically, most of your conversations with ChatGPT are not that interesting, I know. And you can probably delete them and keep most of the context of the conversation by just keeping 50% of the messages, let's say. And another approach, and of course you combine it with the filtering, is to summarize the previous messages and then just keep that summary in your short-term memory instead of all the conversations.
Yeah, and I think the more interesting part is that a lot of the implementation that we've seen used in-memory memory. So like they kept it as some kind of like an object in the computer memory, where when the session is dead, the memories gets released. Whereas if you do persistence, you get a much better experience because the user can go back to the conversation and just continue from the place they left, and this is really, really powerful.
Yeah, and an interesting thing is even though your short-term memory persists, it's still short-term and it's still memory, even though it's in disk and it's long-term in a way, but it's short-term memory still.
Okay.
Yeah, so now going into long-term memory, this memory is memory that, in the particular case of large language models, it can be relevant across different conversations for the same user, so stuff like user information, but it also can be memory that is relevant across different users. And this could be, for example, RAG. So let's look into these memory types in depth. So we have semantic memory. Like I said, this is going to be where we save facts. And this is where, for example, in an agent, it could be a RAG system. This is semantic memory. And then we're going to have episodic memory. And this will be things that I did for a human, but for an agent could be past mistakes it made. That's episodic memory.
And I think that
for
sorry to interrupt again, because I just love interrupting you because I'm from the Middle East. So I think that one of the most frustrating experiences that companies have with these with the LLM applications that they're exposing to the user, even if it's a chatbot, is that it keeps doing the mistakes again and again and again. And I think most of the errors are because they're not really implementing a write mechanism. So the LLM is only reading from the long-term memory. It's only reading from what it knows. It only reads from the retrieval system. I would not going to say retrieval augmented, not going to say that word. So they're just reading, but they never write. And I can understand why companies are going to be a little bit concerned with implementing write mechanism to LLM applications. But I think that many of the reasons why LLM applications are failing to give users the kind of experience that they want is because there is no implementation often of long-term memory writes.
Yeah, I feel like the writing part is very complex. If only we were going to deep dive in it soon. So I guess we can get a lot more context around that. So last type of memory that I wanted to mention is the procedural one. And this for humans, like I said, it's going to be your motor skills, your muscle memory. For agents, it will be stuff like your system prompts. So for example, your instructions on how you perform a task to an agent, that's procedural memory. It's in the prompt, but it's still technically in this architecture memory. But it's long-term memory, but it will be very often injected into your short-term memory. So that's a very important distinction. So like we said, this act of remembering requires that at some point we decide to save stuff, right? Like ChatGPT remembers stuff about us, but we're not aware of what it decided to remember. It doesn't save every conversation with us in some place and then use it all the time, right? There must be some kind of representation of us as users when we chat to ChatGPT.
And you can actually find it, by the way. Some of it you can find the stuff that you remembers in the configuration.
You should probably be able to download it, but that's another question. Like legally, but okay. So we can't use everything like in short-term memory. We can't just take every message we send to ChatGPT. Some users maybe use it every hour, like 5 times. Maybe they have a job that requires them to use programming. So you can't save everything and then expect it to be accessed every time you send a message. This is not practical. So we need to decide what to save and when to save it. And this is a really, really complex task. So there are two main memory creation methods. One is you write during runtime. So you're chatting to ChatGPT and it decides, this is good, I'll save this. Or there is a way to do it in the background. So you're chatting with a chatbot, it doesn't save anything, and then your conversation is sent to a separate chain, a separate LLM that decides what is relevant to save from this. And each of these approaches kind of brings its own challenges. So let's deep dive again. So when updating during runtime, the way you do this, usually, I'm not aware of any other, but the way you do this is you give a tool to the model and it decides whenever it wants to save something about you. So let's say you add something to the prompt saying, whenever the user mentions any personal information, you call this tool and you save it to the memory. And this is exactly how ChatGPT works. You're chatting to it and it knows when to decide to save stuff about you to use in future queries. And this is why it slowly becomes better at talking to you. And when you ask it stuff about you, like you said, Gad, it will dump a lot of information. It's kind of scary, right? You look at it, it's like it knows how old I am, where I live, all this stuff. So the pros of this approach is that the memories are available right away. And you're kind of exposed to the creation of these memories. If you look at the traces, in case of ChatGPT, I'm assuming you probably can't. But in an agent with a graph, you can see when it calls the store memory function, it's very clear what it's doing. The cons is that, of course, if the model is calling store memory, it's not responding to you. So obviously, this will affect latency. And it will distract the agent from doing its job, right? So if it's thinking about, oh, should I save this to memory? Should I not save it to memory? Is this relevant? It's not doing its other job. Maybe if its job is solving complex mathematical equations, it's being distracted, basically. So then we go to the other approach, updating the memory in the background. So if we want to update in the background, of course, there is going to be no latency because it's done after the conversation is done. And it's really good in terms of modularizing the memory logic and the application logic of the agent. The problem is that it brings a whole another set of challenges. So we need to think, when do we write? Do we do like a cron job that every hour checks the user's conversations and you write? But then if you check too many times, it's going to save too many irrelevant things to the memory. So you need to define some kind of schedule and you need to define what is a relevant memory. Maybe you need to create a whole memory architecture that periodically removes irrelevant stuff that it saves. So you see that this architecture starts to becoming very, very complex. And this is really what it takes to build very, very good agents. It takes a lot of infrastructure around simple stuff like remembering who you are. So then that brings me to the, yeah, sorry.
I think there was a question about what is grounding. So we're now going to talk about grounding. We kind of like mentioned it as a very naive way. Maybe we should have paid attention more to it. So Gabriel, if you can focus a bit about what is grounding.
Yeah. So yeah. So the action space is going to be the toolbox of your model, of your agent. So it has four types of actions. 3 are internal. So that's reasoning. And this is very simple. Reasoning is the act of looking at the short-term memory and generating information. So this is calling the LLM, basically. Retrieval is going to be reading information from long-term memory. For example, RAG is going to use retrieval a lot, right? So that's all RAG is. Learning is the act of writing information to long-term memory. And we just saw this can happen live, like when you're running the agent, or it can happen in the background with a very complex architecture. It's still learning. And then you have external actions, and this is where grounding comes into it. For the purposes of this paper and this framework, grounding is the act of interacting with the surrounding environment of the agent. So if you're writing code, grounding is the act of running that code. If you are a robot, grounding is the act of interacting with the physical world. If you are a chatbot, grounding is the act of speaking to your user, assuming that you're trying to speak with that user, and that user is what grounds you, even though the user might be prompting you with any task.
Yeah, maybe to emphasize a little bit about grounding and think, when we talked about long running operations, so you're going to create an LLM system that basically that creates a plan, and then it operates upon top of this plan, and maybe the operation itself is an LLM, and then it responds to this plan. So, you're living in the world of predictions and predictions and predictions. And for me, the idea of grounding, I've seen several definitions, but for me, the idea of grounding is basically to connect the AI system with the ground. So to basically introduce data points from the real environment. That can, like Gabriel said, can be a search on Google. So for example, Gemini can go and search on Google, and then it goes and sees if the results that it's giving you has a reference on a real website. If it's real, like, I don't know if it's CNN, I don't know if you should trust it, but at least it has some kind of reference. So it goes and gives you some kind of reference to the real world, and that's for me the idea of grounding.
Yeah. So getting onto decision making, the last part of this framework, the decision making is where 90% of your agent code is going to be. This is what LangGraph usually handles. This is what Llama Index is going to handle. Also the retrieval, but mostly this. So this process is the cyclical process between doing planning and execution steps. So planning is going to be using either reasoning step, so generating more tokens, or retrieval. So in case of RAG, doing queries to vector databases and all that. An execution is going to be either perform grounding, so interact with your environment, or learning, which is saving stuff to your long-term memory. And this decision making, like I said, is the code around all these toolboxes.
Mm-hmm. Sorry, you jump.
Yep. So yep. So just a final thought about this framework that I wanted to kind of get in, and this is kind of a personal.
How did you manage to go through all this webinar about architectures without mentioning RAG? Didn't you
I
have?
did mention it. Yeah, I
How did
did
you do
mention
this?
in the retrieval, but I
Okay.
shouldn't.
Okay.
But RAG is fine. But I personally don't really like the definition of agentic RAG, and this is kind of a buzzword we see a lot. There is no agentic RAG. It's just agents that do retrieval, and that's all of them. Just the retrieval just happens to be a bit more complex in those agents. So agentic RAG is just you have an agent that decides what to retrieve, when to retrieve it, and uses it as it pleases.
I do think that more than a year and a half ago, we did a webinar again with the same title of Emerging Architectures, and it was 2023, the middle of 2023. And we did say that RAG, we don't think it's a thing. It's more of a search system, a retrieval system. We have seen implementations of RAG in some contexts, but I do think that, when we're talking about real architectures that survive in production, you are thinking about a retrieval system that serves an workflow or an agentic workflow system. And I do like to emphasize that.
Yeah, you don't build your applications around your retrieval system. You build your retrieval system around your agent application. So now getting into a bit more complex stuff that still fits this architecture, we're going to go into multi-agent
about
systems.
Like 4 or 5 slides, right? Before we wrap
yeah, we're just about right done. I know we're a bit out of schedule, but hopefully that's okay.
More complex. Okay.
We're having fun, so that's what matters. So when we want to add functionality to agents, a lot of times we just add a new tool and we add more line graph code and more conditional edges. And very often we start kind of overdoing it. And I know this happened to me a lot at the beginning. And the agent will start to get confused by having 10 tools, 15 tools, right? And it will be performing 5 tasks at the same time. And this is kind of the moment where you think, what if my agent has a tool that is another agent? And this is a huge moment when you start building multi-agent systems and you start understanding the challenges that come around with it. So the advantages of building these multi-agents is that now we can improve a specific task of our agent without regressing in the performance of the other task. So because it's 2 separate agents, we can leave one alone and just improve the other when it needs to be improved. And we can attribute blame to a specific part of our system and even have different teams working on different agents. And this specialization is also really useful because you can give it even more tools, even more context, because it only performs one task really well instead of 15 not so well. And another really good perk of doing this is you get to decide what the agents tell each other. So just going to go very quickly into different types of architectures for these multi-agent systems. So a common pattern, there's three common patterns that I see. So one of them is a network where agents are all at the same level and they can communicate with whatever agent they want. So for example, front-end developer, back-end developer, they're at the same level of hierarchy and they can go back and forth and say, your API needs this, your front-end needs that. Then there's the supervisor or hierarchical architectures, where there's kind of a top agent that instructs bottom agents to do subtasks and more specific. So for example, that would be your software engineering manager telling the front-end developer, you need to do a front-end, and then the manager telling the back-end developer, you need to do a back-end. So there's not necessarily communication between the two types of front-end and back-end developers, but the manager controls both. And then more realistically, there's custom or hybrid solutions. You're not going to develop around a specific hierarchical architecture, a specific network architecture. You're going to do whatever fits your use case. And this is what I see the most often in the wild.
And I do think that once you're thinking about multi-agent systems, try to imagine how difficult it would be to build a graph for each and every one. And probably this is where messages are going to be effective, right?
Definitely. And here we kind of talk about, I just wanted to leave you with a thought of what each agent should see. And then we're going to go over a very brief use case. So when an agent A calls an agent B, we must think, what does that agent need to see? Because certainly the answer isn't always everything. So they don't need to have the same context. So let's say the manager is telling the backend developer to develop a backend. The backend developer doesn't need to know what motivated the manager to want that feature, right? If the CEO spoke to him and then the user sent, like, it doesn't matter, right? All it needs is the context to perform its task. And then when the backend developer comes back to the manager with the feature in his hands, all the manager wants to see is the feature. It doesn't care how you got there. So this is kind of a good analogy to how we should think about this communication. You need to give it just enough context to perform its task and not one token more, otherwise you'll confuse the other agents. This is kind of the example that I wanted to show you. So let's build an R&D group. Let's say we have a simple graph of agents. It's a graph, but inside there's agents with half message. So the user asks a backend agent to develop a backend. And then let's say that backend agent only has the option to ask then the front-end agent to develop a front-end for his backend. So this is a very simple workflow. It's not necessarily correct in terms of software engineering practices, but let's say it exists. So after the backend agent is done with his logic, it's going to need to communicate. And it's going to ask the front-end agent to develop a front-end to his REST API, right? But the front-end agent doesn't need to see the whole backend code. So it just develops his front-end based on the API documentation. And then the front-end agent doesn't need to return all its thoughts about why it decided to develop the front-end the way it did. So all we're left is just enough information for these agents to perform their tasks. And at the end, the user just gets his backend, his front-end, is not even aware that all of this happened. And I think this is a good example of minimal communication getting good results. And I think that's it for my agent.
Okay. Before we're gonna just wrap it up and say thanks to everybody who survived the 90 minutes we were here, especially those that joined from India and Israel. I know I've seen quite a lot from there, so thank you so much. And Jeff, I think. We do have a community. We are running both sites on-site and events on-site and remote. So I do recommend that you join our meetup group. And if you sign up for this one, you're going to get an email with the details and some references, and of course the recording of this one. TensorOps is a Google Cloud partner. So if you are interested in building applications, if you are interested in exploring some of the technologies that maybe Jeff showed here, we would love to hear from you. We can even help with a little bit of credits to test out some of your initial applications. So we would love to hear from you and about your use case and see if we can try to help you get onboarded to Google Cloud. And eventually, what do you see today? So we asked ourselves, are AI systems going to be more autonomous or more continuous? So are they going to be more of these, here's a message, go do this stuff for me, come back 2 years from now with the right answer? or is it going to be more of this continuous operation of collaborating human with AI? We are seeing examples to both. And I think the architectures need to really adjust to what you're trying to build, and the way that LLMs communicate with each other, the way that they communicate with the environment, the way that they're organizing themselves, whether it's doing planning or orchestration, all of that needs to really support the use case, the product vision that you have. We've seen that context and orchestration really are the thing. So LLMs are going to get smarter. Google's going to come up with a Gemini 2 point something and maybe a 3, and I don't know what's going to be the branding of the next model. Maybe Jeff smiles because he knows. But the models are going to get smarter. The whole question is how you're going to connect them to the environment. And you've seen doing it through prompt engineering. You've seen doing it through showing it images, showing it the screen of your computer. So there is many more ways of introducing context into your LLM systems. And what you eventually saw is that they can work together. So if you think about an agent as a unit that does some task, typically, like an agent to answer support tickets, if you're thinking about the next level of AGI, it's going to be organizational level. So you're going to think about AI that collaborates with AI to create organizations. And there, the whole topic of AI communicating not just with humans, but with the environment and with each other and grounding is going to be extremely, extremely crucial. So last word is going to be choose the best fit architecture for your use case. There is not a single one. There's probably one that fits your case the best. And with that, I really want to thank everybody who showed up. And we're going to see you in the next one.